In this clip we're going to work through the steps of drawing a geologic cross-section based on the information provided or shown on a geologic map. A cross-section provides a vertical slice through the earth showing us or revealing what the underlying geologic structure looks like. Now, a geologic map provides all the information we need to be able to draw a geologic cross-section. The map shows a number of different things. The first line of information that our map provides is it shows what the different types of rocks are in the area and where those different types of rocks are seen at the surface. For example, in this map area we have three types of rock shown: a shale, a sandstone, and a limestone. The map shows us where each of these layers is exposed to the surface and where the contacts are, boundaries between different rock types at the surface. So our map also shows us the boundaries or contacts between the different rock types. Those contacts I'm highlighting in red. The geologic map also provides information on the orientation of the rock layers. Orientation of rock layers is described in terms of strike and dip. Strike and dip on the map is shown using a symbol that looks like a squished T. It has a long arm and a short arm. The long arm represents the strike direction. If this is north, this particular rock layer strikes in a northwest, southeast direction. It also shows dip. And dip is basically the angle that the rock layer makes with Earth's surface, which on broad scales is approximately horizontal. Dip has both direction and angle. For example, the strike and dip for the sandstone layer is shown on the map. Where sandstone outcrops on the surface in this part of the map area, its orientation was measured. It strikes in a northwest, southeast direction. This is strike. And it has a dip that's perpendicular to strike. It dips to the west or southwest. That's the direction of dip, and the magnitude is 30 degrees. In other words, the sandstone in this area makes a 30-degree angle. Dip is measured down from the horizontal. Makes a 30-degree angle with Earth's surface. And it's dipping towards the west-southwest. So a geologic map provides all the information we need to be able to draw our geologic cross-section. Different types of rocks, where they're seen at the surface, and their orientation, their strike, their dip direction, and their dip angle. The first step in drawing a geologic cross-section is to transfer all the available information that's shown on our map to the line along which we're going to draw our cross-section. Again, a cross-section is a vertical slice through the ground surface, revealing the vertical structure that area has. What kind of information is shown on the map? What do we need to transfer to our cross-section? Well, the first thing we'd want to do is transfer the location and names of all the different rock types shown in the map area. We have limestone here, sandstone, shale, sandstone, limestone, sandstone, and shale. So what I've done so far is I've transferred the names of the rock layers and the locations of contacts between them based on what the map shows. All I've done so far is reproduced the names of the rock units and the locations of their contacts as shown in the map. I've reproduced that along or on my cross-section line. The next step is to add in orientation wherever it's been measured on the geologic map. In other words, wherever orientation information is available close to our line of cross-section. You can see that the sandstone layer has had its dip direction and angle measured at 3 locations within the map area. The sandstone in this area dips 30 degrees to the west. The sandstone in this area dips much more steeply, 85 degrees, and it dips towards the east. And then in this area, the sandstone dips 40 degrees to the west. We're going to draw in our dips using a protractor. Measure a 30-degree angle and draw a short line representing that dip direction and angle, using again the protractor to draw that dip angle accurately. Doing it here again, we're measuring 85 degrees in the easterly direction. And then here, measure a 40-degree angle and allow that 40-degree angle to dip to the west. Okay, so all I've done so far is I've transferred all the information shown on the map onto my cross-section line. In other words, all I've done is I've reproduced what information is on the map and shown it on my cross-section. There hasn't really been any thought or interpretation involved yet. I'm just reproducing what the map tells me is seen in this area. Names of the rocks, locations of contacts, and dip directions and angles drawn in using a protractor. The most common mistake I see students make is they'll project that dip angle well below the surface. That's not correct because we can't assume that the dip direction stays the same. The dip direction has only been measured at the surface, at the ground surface. In other words, the sandstone dips 30 degrees to the west where it intersects the surface in this area. That dip direction and angle may vary with depth. So just draw a short line representing your dip direction and angle. To draw a cross-section, the next thing we're going to want to do is we're going to want to interpret how different outcrops of the same rock layer are connected above and below the ground surface. And we do that by making an interpretation of how the dip directions and angles change. Again, on the map, dip direction and angle has been measured where the layer intersects the ground, and it may change below the ground. And the portion above the ground has of course been eroded away. It's no longer preserved. It would have been there at some point in the past. So when inferring how your different rock layers are connected and how the dip directions and angles change, don't just limit yourself to what's going on beneath the surface. Also think about what used to exist above the ground surface before that part of the structure was eroded away. In drawing our geologic cross-section, we want to use a pencil because we're not going to get it right on the first try. And as we're drawing our rock layers, we want to try to draw them with a constant thickness. When sediment is deposited to form rock, that sediment is being laid down on some surface like the seafloor or lake bed, And it's laid down in layers that are more or less constant in thickness across broad areas. We can use that fact as we draw a cross-section by trying to draw our units, our rock layers, in such a way that we're not getting radical changes in their thickness. Well, this sandstone, again, is dipping 30 degrees to the west. I'm going to draw dashed lines representing the part of the structure that's been eroded away, where I'm drawing it above the ground surface. Note that I've drawn my sandstone layer with a constant thickness, but I've been changing the dip direction and angle to allow it to go from 30 degrees to the west to 85 degrees to the east. I want to do the same thing over here. Drawing my sandstone at a constant thickness, showing a change from 85 degrees to the east to 40 degrees to the west. Our shale layer, what does our shale layer do? Well, it must do something like this. Shale. Oops. Shale. Shale. This is sandstone. As we draw a cross section, we'll want to keep our rock layers labeled so we can remember what we're looking at. And then what is our limestone doing? It must be doing something like this. Drawing the cross-section reveals what the geologic structure of this area is. We have an anticline on the left side here, and we have a syncline on the right side of our cross-section. Anticline, an upward fold, syncline, a downward fold. This figure shows what the textbook drew for the cross-section, which is very similar to what we just drew. We have our limestone layer, our sandstone, our shale, and we have an anticline in this area and a syncline in this area.